In our last lesson, we talked about the periodic table and how the elements are arranged on the periodic table. And thanks to that arrangement, there are actually several properties of various elements that can be predicted, that the relative values can be predicted based on the relative positions of elements on the periodic table. And we refer to those as periodic trends. And that is what we're going to be talking about in this video. So periodic trends are properties of the elements that can be qualitatively predicted based on an element's position on the periodic table. So we're going to be talking about 4 different properties today where depending on whether one element is like up, down, left, right compared to another on the periodic table, you'll be able to predict if that property is likely to be higher or lower or bigger or smaller. So the first one that we're going to talk about is atomic radius, which is pretty literally what it sounds like. If you think of an atom as a sphere, it is essentially the radius of that sphere. The technical definition is half the distance between 2 bonded atoms of an element. So if we envision 2 atoms, I wanted that bigger, 2 atoms bonded together of the same element, we'll talk about this a lot more in later units, but a chemical bond is actually just when the orbitals in your 2 atoms overlap a little bit, that there is a region of space where electrons from both atoms can coexist. So bonded atoms would look more or less like this. So if we have our nuclei in the center, nucleus, the distance between our bonded nuclei is a better way to phrase this. The distance between our nuclei would be just the straight line between them. So the atomic radius would be half that distance. So that is how it is technically officially defined, is if you take 2 atoms of this element and you create a bond between them, what is half the distance between the nuclei. But you can pretty much think of it as very literally being the radius of an atom. So atomic radius is predictable on the periodic table. We are going to focus primarily on the main group elements and the transition metals a little bit, although they don't follow the trends quite as nicely. That as you move down a family, so I'm going to rough sketch a periodic table here. Something like that, more or less. The largest atom is at the bottom left. So as you move down a family, radius increases. but radius is actually biggest on the left side of the periodic table. So radius increases as you move to the left on the periodic table. As you're moving across a period. So that means that the smallest radius is helium up in the top right-hand corner, and then as we move down and towards the left is where our radius is getting larger. We'll talk about why these trends are the way they are in the next video. For now, we're just kind of introducing that they exist. So our next trend is known as ionization energy. And ionization energy is defined as the energy required to remove an electron from an atom. So essentially what we are doing is we are taking some generic atom, we will call A, and we are turning it into a +1 cation because we have removed an electron from it. So the electron is now kind of a separate entity that we have pulled away, leaving that atom with a +1 charge. So the energy needed to do this is what we call the ionization energy. So ionization energy, okay, I guess I'll just draw it again. Ionization energy is actually highest at the top of the periodic table and to the right of the periodic table. So it is opposite the radius trend that we just talked about. So the lowest ionization energy, which I am going to abbreviate IE, is down here. Highest ionization energy is up here. So as we move up a family on the periodic table, ionization energy increases. And as we move to the right, it increases as well. So we're always increasing as we move upwards towards helium. And a note on just what high ionization energy and low ionization energy means. If we say something has a very high ionization energy, that means it's hard to remove the electron. That you have to put in a lot of energy, you have to pull really hard to get that electron off, whereas a low ionization energy means it's easy to remove that electron. That you only have to put in a little bit of energy, tiny little tug, electron comes right off. Generally things that are easy to change in some way tend to be very reactive. So low ionization energy elements are usually more highly reactive. They're more likely to undergo chemical reactions more easily or more vigorously. So our next trend is electron affinity. Which is defined as the energy transfer that happens when an electron is added to an atom. So it's sort of the opposite of ionization energy. We're now taking an atom, we're taking an electron, an extra electron that was not previously attached to this atom, and we are sticking them together. We are forcing that extra electron into this atom. So the energy transfer associated with this transformation is what we would call the electron affinity. I am going to copy paste this one. Because this trend goes in the same direction, with one sort of caveat, which is that we don't, oops, that is not what I wanted, that we don't generally include the noble gases as part of this trend. So these guys are just not applicable here. It's not that they don't have an electron affinity, it's just that they don't fit the trend with everything else. Because they have filled valence shells, it is much, much more difficult to add an electron into a noble gas because you have to add it up into the next shell, which is going to be much higher in energy. So our highest electron affinity is actually fluorine. I can abbreviate this one EA. And our lowest electron affinity is still francium, down in the bottom left. So the trend goes in the same direction in terms of high-low, but what high and low mean for electron affinity is reversed. So a high electron affinity means it is easy to add an electron. Meaning these are also usually more reactive. And a low electron affinity means that atom doesn't really want that extra electron. So it's much more difficult. So that's why the noble gases aren't really part of this trend, is that as you're moving in that direction, generally your electron affinity is increasing, but the noble gases actually have very, very low electron affinities. They don't want an extra electron because they already have a filled valence shell, which is a stable way for them to exist. But the trend in terms of the high-low otherwise moves in the same direction. So electron affinity increases, moving to the right across a period, and electron affinity increases, moving up a group or family. And our last periodic trend is what's known as electronegativity. So this is something that, again, we're going to come back to a lot more in later units that I like to introduce now with the periodic trends, but it's not going to be super important to us until we get more into bonding. So electronegativity is defined as the strength of attraction, strength of an atom's attraction for electrons in chemical bonds. So essentially, when atoms bond, one way that they can bond is to share electrons, but they don't always share them equally, and whether or not they share them equally is based on electronegativity. If two atoms have similar electronegativity, they have a similar attraction to the electrons that they're sharing. The sharing is pretty evenly distributed. If they have very different electronegativities, the one with the higher electronegativity is kind of winning the tug of war. The electrons spend more time near the higher electronegativity atom. Again, much more on that later. For now, be vaguely aware of what electronegativity means and be able to identify the trend on the periodic table. So essentially, a higher electronegativity means that that atom, that element, has a stronger attraction to bonded electrons. And once again, our trend goes in the same direction. And once again, we don't really include the noble gases. The noble gases very rarely form chemical bonds, so their electronegativities are difficult to determine. In order to determine something's electronegativity, we have to study it as part of compounds, and there are very, very few compounds involving the noble gases, so we usually don't really include them in this trend either, because they don't typically bond. So we have our lowest electronegativity down in the bottom right, and the highest, or sorry, bottom left, highest electronegativity is fluorine, up towards the top right. And then same stuff applies just for electronegativity. I'm going to be lazy and copy and paste things. So this is electronegativity increases as we're moving up a family on the periodic table, and electronegativity increases as we're moving to the right across a period. So in the next video, we'll talk about the physical basis for these trends, why they are the way they are. But it's interesting to see that a lot of them move in the same direction. There's one that kind of goes opposite, but it's all based in the atomic structure. So more on that in the next lesson.